Greeting, dear participants of fifth international workshop of computer modeling and intelligent systems. I'm Vitaliy Larin. Let me introduce my article decision-making algorithm in case of failure of the electric motors of a multi-rotor unmanned aerial vehicle. The safety of unmanned aerial vehicle UAV flight depends on many factors, such as the absence of failure or malfunction of aviation equipment, the absence of exposure to adverse environmental phenomena, and the absence of errors by the aircraft crew and the engineering personnel. These factors are classified in the ICAO risk matrix. Due to literature review represent in the slide 3 and 4, we can conduct the remote firewall will not be able to perform a touchdown operation at a new system defined landing point or return to a departure point. So problem for UAV VTOL type, there are no algorithm for ensuring the required safety during flight in the event of failure of one or more engines. It's this type of vertical take-off and landing unmanned aerial vehicle that will be used for flight at very low level altitude and within dense urban areas. And vertical take-off and landing unmanned aerial vehicle of this type is the most vulnerable to loss of control due to various failures. The development of decision-making algorithms in the event of failure of critical vertical take-off and landing unmanned aerial vehicle components, which include engines, is relevant since it will help prevent an aviation incident. Consider how high the risk of an incident is in the event of brushless motors failure. For technical devices, the most convenient reliability characteristics are failure rate, lambda, and mean time between failure. Lambda can be calculated by two ways. First way, we can use failure rate, and probability of failure-free operation, and second statistical estimation for failure rate. We can use relation of some devices and that fail at our time, and average number of devices that work without failure over time. MTBF is defined as the mathematical expectation of the device operation until the first failure. T is the total operation time of the device, and TI is uptime for the some devices. According to the same sources, MTBF for small electrical machines is in the range of 1,000 to 20,000 hours. MTBF performance of high quality brushless motors is the best among this group. However, there are two factors that influence of which, according to some authors, significantly reduces the specified reliability characteristics. The first factor is the increased rotational speed expressed in RPM. Thus, at a nominal rotation speed of 2,500 RPM, the guaranteed uptime is 300 hours. And when the speed rises to 9,000 RPM, the uptime is reduced to value of 200 to 600 hours. That is when the rotation speed is increased by 3 times. The failure-free operation is reduced by a factor of 5 or more. Therefore, taking this factor into account is mandatory when assessing risk of the incident in the event of an engine failure. The second factor that can significantly increase the likelihood of failure is the ambient temperature. Higher ambient temperature also reduces guaranteed uptime. The dependencies of the decrease in the uptime with the rise in temperature coincide significantly with the dependencies under the influence of the factor of increased rotation speed. Thus, when assessing the risk of an incident, the temperature factor must also have also taken into account. Moreover, the elimination of the influence of the first negative factor can be achieved by maintaining the nominal speed mode during manual remote piloting or by introducing algorithmic restriction when piloting in the autopilot mode. But the influence of the second factor, which is external to the unmanned aviation system, does not depend in any way on the remote pilot's command, and thus must be taken into account when creating various algorithms for onboard systems that make it possible to increase the safety of UAV flight. To implement the algorithm, it's necessary to have a device for monitoring the speed of rotation of the propeller, which is installed on the electric motor. As a similar device, one can use a speed sensor that operates on the basis of the magneto-electric Hall effect. Some manufacturers of high-quality brushless motors already integrate Hall sensors in the motor device, which also serve as positioning support. In this case, the task of providing motor control is simplified. But even if there are no sensors in the design of a brushless electric motor, it's possible to perform local design modifications by connecting an external sensor to each unit. Such a sensor will record every change in the level of the magnetomotive force, which is induced due to the appearances of an electric current in the stator coils. Those information about the speed of each propeller from the Hall sensor will be transmitted to the Vitaliy UAV microprocessor-based flight control system. To implement the algorithm, the number of sensors will be required depending on the number of electric motors of the UAV. Since it's necessary to control all the rotation speeds for each electric motor using their own sensor. The main task of the developed algorithm is to monitor the performance of electric motors even in case of failure, which will identify it in the event of either no rotation or insufficient rotation speed of one or more motors. Since such a failure will immediately lead to a loss of control and the emergence of a conflict hazardous situation, it's necessary to automatically work out a decision on the immediate termination of the Vitaliy UAV mission and its landing. Next device required for implementation of the algorithms is a software modular, microprocessor, or microcontroller. These microprocessors, usually any UAV has two microcontrollers, one for navigation calculation, and the second for is a core or flight control system autopilot. Moreover, the latest trends in the development on onboard system provides for equipping UAV with microprocessor with battery management system, which make it possible to increase the level of Vitaliy flight safety. With regard to the choice of necessary hardware, the block diagram of the decision-making algorithm will have the following form, represented on the slides 6 and 7. At the first step of the software implementation of the algorithm, it's necessary to set the failure counter X for the I engine. The event counter is reset to zero during the initialization. During the initialization of the onboard control system before starting the flight. As a failure criterion, we will consider an event whereby the current value of rotation speed of I engine, where rotation measured with I sensor will be less than required value of V, where requirement is even equal to zero, necessary to enter the controlled flight of UAV. As long as the flight in progress, the algorithm provides for a cycle pole of the rotation sensors and compares the current measured speed value with the set value generated by control system. In the case of the first fixation of a failure of one of an electric motor, the counter of the I motor failure is incremented for the first time and takes the value equal 1. After the initial setting of the failure counter, a reconfiguration check is performed, and if this check gives a negative result, the transition to the next step of the algorithm is performed. In this case, such an electric motor is considered to be conventional file, and information is sent to the control system about the repeated sending of control action to this regime in order to establish the required value of its rotation speed. The control action is usually a pi-flight modular signal, the required pulse with which is set by the microprocessor of UAV control system. If the condition V rotation less than V requirement is repeatedly satisfied, then the failure counter takes the value xi equal 2, and the transition to the algorithm branch responsible for the emergency termination of the flight occurs science when one electric motor is inoperative. The probability of the origin of an aviation incident increases. The emergency command block must contain two sequential procedures. In the event of failure of one of the engines, the multi-rotor type UAV immediately loses stability and begins to rotate around a horizontal or vertical axis. If at this moment in time all the engines are stopped at once and then the parachute compartment is open for such an unstable VTOL UAV, the parachute will get entangled around the hull, and the VTOL UAV will still make an uncontrolled fall, thus increasing the risk of an incident many times over. In case of failure of one of the engines of the propeller driving group, to stabilize the multi-rotor aircraft, it's necessary to immediately shut down the symmetrical engine, which is located diagonally opposite the suddenly failed engine, according to the diagram represented in the slide number H, where symmetric engines for a 6-screw VTOL are connected by blue, red, and green dash, respectively. After such a shutdown, the motors remaining in working condition will stabilize and prevent an uncontrolled fall for some time. Thus, in the branch of emergency subroutine, the emergency engine is first assigned a zero index, J equal 0. Following that, the symmetrical diagonal motor is turned off. The index of such an engine for a quadrocopter will be x2, for hexacopter x3, for an octocopter x4. To unify the algorithm in the block diagram of the algorithm, the symmetric motor indexed is denoted as symmeter. After this operation, a short time delay of no more than 3 seconds is required to stabilize the aircraft. The block diagram of the algorithm shows this delay as the delay statement. Further execution of the program involves sending a command to the flight control system to simultaneously turn off all other electric motors, which in a formalized form can be represented as a command V-rot equal 0, executed in its cycle. Next, the sending of the current coordinates is initiated, at which the flight is forcibly interrupted via the downstream SIDWA subchannel to the remote pilot to notify him of the location of the UAV, and a command is sent to the control system that initiates the opening of the parachute compartment and the release of the parachute. Then VTOL UAV makes landing. You can see conclusion for this article, you can see that I stopped my presentation. Thank you for attention.